Welcome. In this video, we're going to show that the sum of consecutive cubes is equal to the sum of consecutive integers all squared. And this formula turns out to be true for every n value bigger than or equal to 1. And we have a little bit of a hint about how to write consecutive integers to help us along the way. So the method that we're going to use is the method of mathematical induction. So to start off, we need a base case. So for our base case, we're going to show that the statement of the equation that we're given is true for n equal to the smallest case scenario, which is 1. So we plug in 1 on the left, we get 1 cubed, and we plug in 1 on the right-hand side, and we get 1 squared. So our base case checks out, and we can say, therefore, p, when we sub in 1 for the n value, gives us a true statement. So let's remember this variable p sub 1 or p sub 2 or p sub 100. It's a true or false variable. It's not a number variable, like n represents some integer bigger than or equal to 1, whereas p represents what we call a Boolean variable that's either true or it's false. Okay, so moving on to our inductive step. So our inductive step, I always like to write down what we want to show. So we're trying to show that if p sub n is true, then p sub n plus 1 is true. And let's quantify for which n values do we want to do this for. We want to do this for n values bigger than or equal to 1. Now, to give you a snapshot of what this does or why this proof works, if we know that p1 is true from the base case, and we've proved that we can imply that we can bump that 1 up to 2, then we'd know that p2 is true. If we knew that p2 is true, then we'd know that p3 is true, and so on and so on and so on. So you can see it's like a domino effect. When the first domino knocks over, the next domino also falls over, the next domino falls over, and so on and so on and so on. Okay, so in order to complete this goal, let's try to write down what we need to show to make this happen. Let's just write down the mechanical parts first. So what we need is the sum of consecutive cubes, 1 cubed plus 2 cubed, all the way up to n plus 1 cubed. So we have n cubed and then finally n plus 1 cubed. Our job is to show that that's the same as 1 plus 2 all the way up to n plus 1 all squared. So our inductive step would be complete if we could show that these two expressions are the same. Now we get a little bit of extra help along the way. We get to use p sub n. P sub n says that the sum of consecutive cubes up to n is equal to the sum of consecutive integers up to n all squared. And in fact, we have that right here. If we look at this first portion of the first expression, we can use p sub n right there. So by p sub n, we know that that first part is equal to 1 plus 2 all the way up to n all squared. Okay, now in the question, it also gave us a hint. In the question, it said that the sum of consecutive integers has a formula. So let's use that formula now. So the way it works is if it's 1 going up to n, then that's the same as n multiplied by n plus 1 divided by 2. So we can replace all of that inside of the brackets. And the expression below, well, we can replace the same thing. We're just going up to n plus 1. So this one would be n plus 1 multiplied by n plus 2 all over 2, and then all squared. Okay, so we're getting these two expressions closer and closer together. There is one important step to kind of complete here. Comparing the two expressions, So if we look closely, lots of things are already the same. The biggest problem here is that we have two terms. Two terms here, and down here there's just one term. So how can we change that so that we'll just have one term up here? Well, the idea behind that, as usual, is factoring. This form down here is completely factored. This form up here, we could still do some factoring to try to make it look the same as the one down below. Let's try to look for some common components to factor out. Well, there's an n plus 1 squared here and an n plus 1 squared here. And on the bottom, there'd be a 2 squared. Let's factor both of those things out, so hopefully what's left over will match up, and we'll be able to say, yeah, those two expressions are in fact equal. So factoring out an n plus 1 squared over a 2 squared on the bottom. And then we have a big bracket with everything that's left over. So in the first term, we'd have an n squared left over, and that's really it, just n squared. And in the second term, we'd have an n plus 1. It was to the power 3, but we pulled two of them out, so there's an n plus 1 just to the power 1 left over. Okay, and we also pulled out a 1 over 2 squared, or 1 over 4 if you like. So in order to make sure that we've factored this correctly, we're also going to have to multiply by 4. Now, the last thing that we want to do is verify that our remaining chain of equality, that remaining link that's right here, is in fact true. So let's overview. We have the n plus 1 squared. N plus 1 squared is there. We have 2 squared, and 2 is being squared down below as well. The only thing that we're left to verify here is that the n plus 2 squared gives us this. So let's do that. Let's just make sure and verify that that happens. So n plus 2 squared, if you expand that out, you get n squared plus n multiplied by 2, so that's 4n, plus 2 squared, which is also 4. So this guy here is the same as that guy right there, and everything works out to complete our inductive step. So we'll just get rid of the items that we don't actually need to finish off our proof, and we'll write our closing statement that says, therefore, p sub n plus 1 is true, and this completes the induction.